Hi, my name is Vijay and I'm excited today to be talking to you about widening access to applied machine learning with TinyML. Let me first and foremost start off with what we are talking about when we say machine learning. Now, machine learning is a subclass of the artificial intelligence field and specifically deals with trying to look for patterns in data. Over the past couple of years, one of the things that's happened is that this notion of deep learning, as we call it, which basically uses neural networks, which tries to mimic how our brain works, has been growing tremendously, and this has enabled a wide range of applications that you and I, by and large, take for granted today. It's used for vision processing, it's used for understanding speech, it's used for recommending things to us based on our behaviors. For example, you can look at this picture and say, is it a cat or is it a dog? The machine learning algorithms get this right quite a bit. They can actually say that this is actually a cat all by themselves. Object detection, being able to precisely pinpoint where in this image, for instance, is the apple or where exactly is the orange. It comes in very handy for use cases like shopping, for instance. If you see something interesting in an image, you want to be able to click on it, and that allows you to then generate value for the consumer. Or things like segmentation, where in a given picture, you can precisely point out what are all the pixels that correspond to a person or a car or which corresponds to the road. Now, this is very useful, for example, in use cases like autonomous vehicles. Machine translation, being able to read web pages, for instance, that are written in some foreign language in a language that you understand, right? Or recommendations. For example, if you watch Netflix, there's a recommendation machine learning algorithm that's continuously learning, that is learning to recommend things that you would likely want to watch again in the future. Same with Facebook, for instance, knowing which posts are likely to actually interest or engage you. Now, a lot of these capabilities are really enabled thanks to the data centers that we've been building. Now, these data centers consume a significant amount of power, so much so that they are called warehouse scale computers that are literally built next to dams in order to just power them efficiently. Our thirst for this system space has been so much, especially in the last couple of years, that we have now this two eras of machine learning, as we call it. Specifically, the era that came after 2012 and the era that was before 2012. The key thing that happened at 2012 was this innovation called AlexNet, which is this remarkably powerful capability of running machine learning very efficiently on GPU hardware, which unraveled a whole new generation or capabilities in terms of training these machine learning algorithms. The computational desire has suddenly become so thirsty because of the innovations that AlexNet enabled that it outpaces how we have historically been doing things. So this basically means that machine learning is growing at a remarkable pace, and there's a dramatic thirst for computing horsepower here. And therefore, companies like Google and NVIDIA, for instance, have been specializing a lot of their processors in the computing hardware in order to unlock this capability. So much is the demand for this that now we're starting to even look at new technologies in order to do the computation much more efficiently. For example, a company called Light Matter that grew out of Boston, out of MIT here, is specifically looking at how to do all the machine learning computation in the photonics or light domain rather than doing things in electrical. So it's mind-boggling as to how excited we are about this potential machine learning, that we're looking at all kinds of different use cases and devices that are needed. However, today I'm going to say that bigger is not always better. There are certain areas where, especially in the context of low resource domains, where bigger is not always going to get us the most bang or value for the money. One of the reasons is really because machine learning systems are starting to consume a significant amount of energy. For example, in order to train a machine learning algorithm that, for instance, might be able to understand what I'm saying, in order to do that, it might very well take the same amount of energy that this 747 takes in order to fly from the West Coast to the East Coast and back again. So machine learning's impact on climate is starting to become a very prominent thing. So for example, this paper here basically says that if you want to train a transformer network for natural language processing, it is going to consume 5 times the carbon footprint of a car over its lifetime. So that's remarkably astounding, right? So what we're increasingly seeing is that the machine learning capabilities, due to some of these reasons, are moving away from data centers and more locally to us, because then we can enable more intelligent and efficient use cases where the data resides. So, for example, you might be taking a picture, and very often when you take a picture, this picture is naturally enhanced, right? Now that's a very important application because many of us take lots of pictures. But machine learning is actually enabling a lot of societal good as well when we enable such technologies at the endpoint. For example, here's a video of what's called Planet Village. I'll let the video do the talking.
Cassava is a really important crop. It provides for over 500 million Africans every day.
Cassava is a good source of nutrients. It can withstand harsh conditions, and because of that, a lot of people are farming it. There are several diseases that affect cassava, and they make the roots.
And these diseases are reducing the cassava crops by between 40 and 100%. So we're trying to use machine learning to respond to those diseases.
The app that we've designed can diagnose multiple diseases. You wave your phone over a specific leaf, and if it has a symptom, a box will pop up saying you have this problem. When you get a diagnosis, you learn about the best management practices. We're in a very rural location. People don't have access to internet, and TensorFlow is the only platform out there that can allow us to build these advanced models but deploy them onto a phone.
Because out in the field, we need to give the farmers the access to the information immediately.
So that's one beautiful example where we're seeing that as we move machine learning technologies onto the handset, we can enable a lot of societal good. Now, increasingly, one of the new trends that we're seeing is that this sort of machine learning capability is moving not only just from your phones. In fact, it's starting to move more into smaller devices, things that sort of surround us, like our watches or toothbrushes, and all the devices that are around us, consumer electronics and so forth. Now, this opens up a whole new range of capabilities, and that is because these kinds of devices, when you deploy machine learning at that endpoint, have a lot of benefits. For example, because a lot of these kinds of devices often have bandwidth constraints. We can't stream all the data that these devices are continuously sensing or observing up into the cloud. That's going to drain us out of energy. So we need to process that data efficiently. So we want to be able to use machine learning as a means to filter the data. Reliability, we cannot always assume connectivity. For example, in the Plant Village video, the lady just said that we cannot always assume we have network access. Latency, assuming that you can ship the data somewhere else is actually going to take a long time, because you need the results sometimes to come back very much immediately. Privacy is becoming a very important problem because we want to keep the data local. We got to have the people who are generating the data own the data and know how the data is being used. And energy. Energy is a critical thing because often a lot of these devices are operating on coin cell batteries, so they don't have a lot of energy to expend. It's not like a device can be plugged into the wall at all times. So we're seeing machine learning coming out into a lot of these kinds of state-of-the-art devices. That said, later on I'll show you how this sort of capability is now starting to increasingly be moved out into rural areas where we can actually generate much more impact and value. And that's really where tiny machine learning comes in. TinyML is one of the fastest growing fields of machine learning, and it's all about machine learning algorithms, embedded hardware, and embedded software coming together. And the key goal is that we want to do on-device sensor analytics. Embedded devices like the ones I showed you, have a lot of sensors in them, but often we don't make use of that sensor data. And what we're trying to do now is increasingly try and do on-device sensor analytics so we can extract useful information. Now, we want to do this with ultra low power consumption because we want to run this machine learning capability all the time so we can get useful information from a large number of devices and turn that information into something that is very constructive that can drive consumer products. And ultimately, the goal is that we want to do all of this on battery-operated systems because battery operation enables us to deploy them in rural areas or far-reaching places. So the most common use case of TinyML is probably something that you already deal with when you say, OK, Google, for instance, or when you say, hey, Siri. That's an example where you're already interacting with TinyML because the system is detecting the keyword Siri or Google and so forth. Or perhaps you use Amazon Alexa. So when you say Alexa, that's an example where TinyML is actually working in practice. But that's just the beginning. There are lots of different applications in robotics, augmented reality, biomedical applications, brain sensors, and so forth, where this sort of machine learning, if we can enable it inside these small little embedded systems, can enable a whole new wide range of cutting-edge applications. But the ones that really interest me, though, are the ones that really help us take care of our planet. Things where there are hard problems to solve, where only if we can embed devices that have intelligence capabilities at the endpoint, we can actually solve them. So let me give you a specific example. So this is a project called ElephantEdge. where a large number of different companies are deeply involved in trying to save elephants from poaching and so forth. Let me give you an example. This is a video that I'm going to play real quick, which is all about doing elephant tracking in order to help understand how elephants are moving out in the wild. Now, this is a video that's actually from very early years.
Although GPS seems ideally suited for tracking elephants, it'll require the world's biggest radio collar.
The collar is made of double layers of machine belting which are stuck together with a strong glue, and it has double washered rivets the whole way up and down. Experience has shown us that it gets extremely hard wear from the elephants. It gets rubbed and smashed against rocks and rubbed against trees with tons of pressure behind it. At the bottom, stuck in a block of acrylic, is a conventional radio transmitter. There's also some batteries, and the cable goes up the spine of the collar all the way to the place where the GPS is going to sit up here, pointing up towards the satellite so it can receive the signals.
Now, that's an example where we're actually using technology in order to help save the animals. For example, if we can track the elephants, then we can do risk monitoring or conflict monitoring. Risk monitoring is knowing when an elephant is moving into a high-risk area and sending some sort of real-time notifications to rangers so they can take some action. Or prevent the elephants from actually getting into a conflict with farmers, for instance, because humans and animals need to live safely. So if we can do tracking, we can enable a rich kinds of different use cases. But we can actually go much further than those kinds of use cases if we have embedded machine learning. Let me give you an example. If we can actually sense and tag the creatures, then we can actually try and understand what their activities are. By using machine learning, we might be able to say, are they eating, are they sleeping, are they drinking, and so forth. We might also be able to understand how they communicate. For example, let me give you a very specific scenario where if we could just record the sounds and understand the sounds, what we'd be able to enable. Here is an example from the Elephant Listening Project, where if you had machine learning capabilities and you could listen to the sounds in real time, you would know what the creature is suffering with. So in this example, it's an infant that is searching probably for her mother, and you hear the same sort of pattern in the sound that's repeatedly emerging. But these are real-time signals that need to be tracked on the fly. Now, if you try to capture this data and offload this data, that kind of processing doesn't work. But if you had tiny machine learning where you have a small little sensor that's strapped right there and it's actually able to process this real-time information coming through, then it would be able to figure out, for example, this infant might be lost or in trouble. And this way we'd actually be able to take proactive measures in saving these creatures. Not only that, we might actually be able to do something very constructive in terms of helping them reproduce and so forth. So the applications around conservation are remarkable. Now, this is a project that is actually being done by OpenCollar. Now, earlier I showed you Ian's version of the collar, but you can see these smart collars which actually have machine learning capabilities embedded on them can actually last for multiple years from a single battery unit. So it's a remarkably powerful sort of technology that we're starting to unlock in order to do a lot of social good. Here's another example, for example, that I know a colleague of mine is doing at Harvard, which is talking with whales, where the goal is to help understand those sounds that these whales make by embedding them with small little sensors that don't harm their skin but can actually be on their surface. And by actually understanding the signals in real time, we can actually try and extract out the language semantics, for instance. Of course, there are many other use cases. For example, we can do smart agriculture by embedding soil sensors where we get the data back and we can actually do real-time analytics to be able to figure out, for instance, when to water, when not to water, and so forth. So there's astounding kind of capabilities that we're starting to unlock at this point. And the key message that I'm really trying to get to is the fact that we don't want to leave any good data behind. And that's what TinyML is all about. If you look at the volume of data that these IoT, Internet of Things sensors can actually generate from all the embedded devices that are out there, less than 1% of that data is really what we're actually using today. And already we take machine learning examples, machine learning application for granted. This is why I'm showing you all those rich kind of application use cases. They have already changed our world. But imagine if we could actually leverage all of the data that's at these endpoint sensors. Imagine all the different use cases we can enable to make the world a better place. So, in summation, there are a massive number of opportunities with TinyML across many different market segments. And I think like one of the interesting areas is going to be around unlocking the capabilities for humanitarian good. And I'll get more into that later on. Let me touch a little bit in terms of some of the technology kind of opportunities and challenges we have, just to give you an idea of what needs to happen in order to be able to democratize this sort of machine learning capability so that we can enable this at a wide range of devices. One of the key things is that a lot of these devices that are actually going to be running this sort of embedded ML are small little sensor-based devices like the examples that I'm showing you here. Now this, for instance, is as small as your finger. Now just to show you a concrete example, I'm going to hold one device up and you can see that this computing device literally fits in my hand. Now these devices are remarkable because they can actually operate on just a simple coin cell battery, and they can usually last a year and so forth. A lot of innovation is being done around this space. There are a large number of these devices that are already out there. In fact, there are over 250 billion of these microcontrollers out there. And so the fact that they're out there and another 30 million are likely shipping just this year alone is an astounding opportunity for us to enable embedded machine learning everywhere. But there are some challenges that we run into, and I want to talk a little bit about them. So generally, when you have a rich heterogeneity of these different devices, because they have to operate on the battery power, often are extremely lean and mean in terms of how they're actually designed. So this leads into challenges around embedded hardware and embedded software. I'll touch on the embedded hardware side first. Usually you have a wide range of different microcontrollers that are actually there. Now, for folks who have done computer science, you'd often know that like when you're dealing with these embedded hardwares, if there are a lot of different microarchitectural differences there, then deploying the code that runs on one device onto another device is extremely challenging. Now, another challenge you get into is the fact that they don't have much memory. Often these microcontrollers only have around kilobytes of memory. And because of that, they're able to run for a very long time on coin cell kind of battery. However, the memory constraints make it extremely hard to deploy big, complex machine learning models. You have to make them very small and efficient. And of course, power is extremely critical. And often you have to decide how much power you're allocating for computation, for running the machine learning algorithms, versus how much you're actually allocating to do communication, to actually send the information that's actually useful up to some place. So you have to be very conscious about this. And then of course there are software challenges. For example, simple things like allocating memory, something that we don't think about on a daily basis when we're using big computers, are actually extremely challenging because there's a lack of portability in libraries, because every single library is designed for a particular embedded system. And of course, you might not even have operating systems. You might be very familiar with the Windows operating system, the Linux operating system, or the Mac operating system. By and large, those are the three big operating systems that run the world. When it comes to embedded systems, there's no guarantee about that. Because they have to be lean and mean, they're often extremely specialized, which makes it really hard to write code in a way that's actually portable across these different devices. That's what I'm getting to. Now, there are ways to deal with this. One of these things has been like this project that we worked on, which is called TensorFlow-like Micro, which is specifically designed in order to take neural networks and be able to run them on small little microcontrollers with only a handful of kilobytes of memory. You can run intelligent machine learning models with just like 16 kilobytes of memory, for instance. And the code that you write on for running on one device is actually fairly portable across multiple different devices. Now, I won't get into all the nitty-gritty engineering details around this. I encourage you to read the paper if you're interested in, but it's got some really remarkable characteristics. And the key point that I want you to take away from this point is that we have the necessary machine learning tools in order to be able to widely deploy machine learning across a range of embedded devices. And that is possible if you use frameworks like TensorFlow-like Micro. That's what I want you to walk away with, is that today you can go out and you can actually build machine learning models and deploy them on embedded devices. Now, the next thing I want to focus on is around data. Now, often when we talk about machine learning, we tend to focus on a very small portion of a very complex pipeline. For example, what I just talked about with TensorFlow-like Micro is specifically around designing models and training models. However, in reality, a machine learning pipe goes all the way from having data engineering principles, to actually deploying things and actually getting feedback. Now that is a very complex pipe. And often a lot of folks just focus on just the machine learning training model part. And this leads into us having challenges when we actually want to deploy things at scale. Specifically today though, I want to focus on the need for us to think about how we collect data and do things around data much more efficiently and carefully. Because I think like without the data, there is no machine learning that you can actually leverage. Remember, because machine learning ultimately requires a large amount of data in order to learn behavioral patterns. Let's take a very specific example. For example, when we say, hey Siri, what's the base denominator in here? The base denominator is the fact that this is in English, right? But here's what I think about. This notion of having these speech commands, as we call them, why should they be restricted to just a certain subset of languages? There are over 7,000 different languages spoken across the planet. And yet, when you look at machine learning technologies, it's only limited for a handful of languages, like Spanish and English and German perhaps, and so forth. So, how do we actually reach for the data? Now, machine learning typically needs a lot of data, is what I was saying. But as you look at a large number of the population, as you increase the number of people you want to cater for with these kinds of technologies, what you will find is that the data basically diminishes very fast. This is because we don't have data sets. Now, typically, in order to build a machine learning model that recognizes, for instance, when I say yes or no and so forth, you have to go through what's called data engineering, where you have to gather the requirements for the kind of data you actually want to be able to study. For example, if I want the machine to start understanding yes and no, I have to define that as a key requirement. Then I actually have to have a lot of people go out and give me many different accents, young kids, old people, mid-range people, and so forth. You have to collect a lot of data, thousands and thousands of samples. Then you got to make sure that the data is actually valid and it's actually correct. And over time, the data experiences drift. In other words, the demographics of the population change and so forth. So it's a very complex thing. You have to have that data. Without that data, you really can't do much. Now, that begs into this question of how can we enable this sort of like keyword spotting application for a large number of different people? This leads into this challenge of keyword dataset generation. Rather than manually collecting data, which is what is done by state-of-the-art companies and so forth today, we need to start building automated keyword dataset generation pipelines. Now, this is just one example I'm going to give you here, the couple of other works. Recently, we released this paper called the Multilingual Spoken Words Corpus, where we wanted to democratize this kind of like tiny machine learning around keyword spotting for many different languages. We want especially low resource languages. So we released a very large corpus for 50 different languages, over 6,000 hours of data, and it's all automatically generated. Now, how do you do this? So, well, for example, let's say if I want yes, no, or up and down, I would just specify that these are the words. And the system automatically goes and finds different sentences, spoken, transcribes, speech sentences that are out there, and extracts those full sentences. And out of those full sentences, it finds the key words that you're interested in, yes, down, up, no, and cuts those little bits and pieces out, and dynamically synthesizes these audio clips that are all needed. So think of it as a search engine, think of it as a Google engine in order to be able to build these keyword data sets. What this allows you to then do is to be able to train a keyword spotting model in any language, which is remarkably powerful. Now, just a little bit about the data sets. You'll see that we cater for a large number of different resource languages, from low resource languages to medium resource languages, all the way to high resource languages. So this gives, in many sense, for many different languages, the first time there's actual data available in their language in order to be able to train these kinds of keyword detectors, which can actually enable a wide range of use cases. Just to be more specific, these are like the 50 languages, for instance, that we recently released. And you will see that for some languages, there's a large volume of audio clips. You need a lot of spoken data in order to be able to train machine learning models. But in some cases, we have very little data. Now, don't let this fool you though. Very little data can actually be remarkably powerful if you know the right kind of network to create. For instance, recently we released what we call as a few-shot keyword spotting in any language, where the key goal is to support low-resource languages where you might not have these large corpuses of data. Without getting too much into the details of a paper, which you can find in InterSpeech this year, the key nugget is this. We first train a large multi-embedding model based on data that we actually have in, say, 9 different languages. And we create what we call as an embedding representation. You can take this embedding representation, and then for a low resource language, you might collect just 5 target keyword examples, like saying yes and no in a certain language. And just with those 5 keywords, you would actually be able to detect whether that word was said. That's like saying, I can say, okay Google, or I can say, hey Siri, in a completely new language that I've not seen before, with just 5 examples, which is remarkably powerful. And I just want to tell you that this kind of technology actually works really well in democratizing TinyML, because if I look at training the machine learning model on languages that I've actually seen the data on before, I can do very well with about 95% accuracy. But the key nugget is if I'm looking at languages that I've never seen before, even on those languages, I can actually achieve very high accuracy, which is really remarkable. The fact that the system, that the neural network has actually never seen the language, and yet it's actually able to recognize with a handful of samples, is a very powerful concept. Now I want to show you, for example, how this could be used in order to enable some very interesting use cases in low resource communities. What I'm showing you here is what we call as a multilingual keyword spotting visualizer. Now let's say, for example, I want to detect this word, akuaka. And what I want to do is that I have some sort of, let's say I have a problem where for example, I need to be able to figure out where in my region, for instance, there might be a health issue. Right? Now, what I want to be able to do is I don't have enough resources to be able to send people out into all these different regions, because that's a lot of nurses and doctors who actually have to physically go and be able to gather information. Instead, what if I could just tune into the radio frequencies out there, so that by listening to the radio transcripts, and if I detect certain keywords, like for example, where if there's a health issue, be it a mask or akuaka and so forth, then I can automatically build a demographic profile. So let me show you, for instance, how this works. The key idea is that there's a transcript that is going by, and you want to be able to detect this word just by giving it one example.
Tia China olwalerezeemu okwambalira ginnaye y'Amerika olw'okumetta China enziro nti ye yakola akawuka aka coronavirus akatuze emmere enkya ezigenda okungulira ebijimusa n'omusanga ng'ali awo ebintu tabitegeera oluusi ayogera yekka lakikaba naddala akawuka akaleeta mukenenya.
So what we're seeing is that in this kind of language where I don't have a large corpus of a data set, but if I have this embedding model that I just showed you, and I just give it like a few examples, like 3 examples or 5 examples, then in a long audio stream, I can actually pick these keywords up. And if I can pick these keywords up in a radio broadcast, then I might be able to dynamically build a demographic map of where are these kinds of words being said, so that I might start getting an idea, it looks like this region actually is suffering from some sort of health issue. Now that's a very powerful thing to be able to do. Now, there are many other things that you can actually enable. Now, this is all exciting technology, but one of the key questions that I have in mind is how can we get more people embedded into this space so that we can actually get the next generation to be able to use this sort of technology to uncover or unleash the new application use cases that will transform the world. That leads us all into education. Now, when we look at machine learning, and we look at machine learning courses and education out in colleges and so forth, you will find that there are a lot of courses for general machine learning. Right? But the reality is, for a lot of these embedded systems, of which we have over 250 billion of these devices out in the field, we have very few. In fact, nothing's really out there. So I'm very passionate about getting us to build a community that actually knows how to use this kind of technology that is on the horizon. To this end, we have been working in collaboration with Google to actually build an entire new course series and made it publicly available on edX, free of cost if students want to take, so that they can actually learn what embedded machine learning is about, or TinyML is all about, and go on to build applications. One of the key things that we do is focus on this end-to-end complete stack, going from understanding the value of data, for example, in the use case that I just gave you, all the way to physically deploying it on embedded devices. And we structure these things in terms of modular design of courses, where we go from Course 1 just talking about the fundamentals of TinyML. Course 2 talking about what are some interesting applications like the examples that I gave you. Course 3, physically deploying things onto an embedded device. Now, in order to make this, we actually built a custom kit so that students can physically learn how these embedded devices work. Not only that, they're then going to deploy machine learning on top of them. So we try to make it a very hands-on sort of an activity so that students can actually engage with this. And one of the key things as we do is that we actually try and make sure as you're teaching these young generation how to use machine learning with sensors and so forth, you got to be very responsible. You got to teach them that any kind of technology can be used for good and bad, and that they have to understand what the implications of their deploying AI is on these devices. And when we structure this into every single course. Now, this course is actually taken very broadly, and one of our goals is really to outreach to as many students as possible, no matter where they are, in terms of getting them on board. In less than 1 year, we've had over 50,000 students take this course globally. Now, but that alone also is not enough, because it's one thing to disseminate the information out to students. Another thing is to actually teach the teachers so that they can actually go ahead and teach their own students. And so to that end, we have set up this TinyML Open Education Initiative, which is open for anybody to join, where the intent is that materials are actually shared and we build a community that is passionate about teaching this and understanding what these capabilities are so that we can unlock the future. We also have dedicated working groups that specialize, for instance, only on like certain topics. Like TinyML 4D specializes on tiny machine learning for developing countries, where getting access to some of these resources and cutting edge material is actually hard. For instance, at the TinyML 4D activity, what we have done is we've actually gotten representatives from very different places across the planet to participate from their universities in our TinyML 4D activity, so that we can give them free kits so that they can then share them with their students and so forth. This requires a global effort, because we had to work with the United Nations and UNESCO folks in order to be able to ship these kits without having the penalties of taxes and customs and so forth actually being hindering the actual educational outreach here. What I've talked about today is like why I think the future of machine learning is tiny and bright with TinyML, and how these embedded systems have the potential for not only enabling new technological use cases like augmented reality, virtual reality, but they actually have the ability to impact us in a societal level, where they might be able to help us with conserving nature and so forth. And another thing that I've focused on is what are some of the technical challenges that we have to address, be it in terms of the hardware heterogeneity or in terms of the actual data. Now, these two are just samplings that I'm trying to give you, but there are a large number of different things that can be done. This paper that we recently released actually talks a lot about the underpinnings of some of the things that I've actually touched upon in this talk. So if you're curious, I strongly encourage you to go check it out. With that, thank you very much, and I appreciate your time.